All right, in this video I'm going to be talking to you about the epsilon delta definition of a limit and the definition of continuity. And this is a much more precise definition of a limit. I don't know if you remember in the AP calculus class, when I went to define a limit, I really didn't, especially the limit from one side. Okay, we said that the definition of the limit existing was that the one-sided limits existed and agreed. Okay, but the definition of a one-sided limit itself was very vague. It was like, the closer you're getting along the side, it's like whatever you're headed towards. Okay, well, we need something a little more powerful than that. And this is something that, mathematicians wrestled with for quite a while, these precise definitions of continuity. And it wasn't really until, I believe, Karl Weierstrass that really put some formal boundaries on, what can we and can we not do. Really, he was the guy that added the logic to all this stuff. So, the definition of a limit. Okay, we say that the limit as x approaches c of f of x is equal to L if we can get as close as we want to L by taking values of x sufficiently close to c, right? That's the whole idea. Let me just again draw you a picture of what this means just to remind you. This is the limit existing and equaling L. This is the point C and L, I guess. It's not there. And what I'm going to do is I'm going to say if we want to get close to this y value, we just need to take x values close to x equals c. Now how we're going to formalize that is if for every epsilon greater than 0, there exists a delta which depends on epsilon. I like to put a little subscript for epsilon, but just to remind you that it depends on epsilon, when you go through to actually compute these. There exists a delta which depends on epsilon so that anytime we're within delta in the x range, we will guarantee to be within epsilon in the y range. So that if x minus the x value we're interested in is less than delta, then f of x is within epsilon of the limit. Whoa. Okay, now this is the type of thing that is tough for me to draw pictures of, but there are a number of really, really good animations on the internet. Okay, so I think I'm going to take this little image and I'm going to erase it and draw it out bigger down here with kind of some axes for scale. So we've got ourselves a curve, and I kind of liked the one that was kind of going up like that. It had a little hole in it, and then it continued to increase. Okay, this is x equals c, this is y equals L, just to use the same terminology I had up here. And what I'm going to say is that the limit existing means that, if I need to be within some range of L, say epsilon, this distance right here is epsilon, well then I can, okay, that was supposed to be, nice straight lines. I can guarantee that I'll be within this range, provided that I am over here in the x's, right? As long as I'm over here or in here. So for these, I believe that your delta would be the larger of these two distances. I believe it would be that. So if we're within this distance of c, I can guarantee that we'll be within epsilon of L after we run these x's through f. Okay, that is the idea. And then I can squeeze these red bars down closer and closer, and then that will necessarily move these blue bars closer to c. And I can make that epsilon as small as I like, right? Because this is just such a small hole. Okay. Again, I could go a whole lot more into detail about this, but I've seen animations where they have these bars and they're kind of shaded, and then they squeeze this, and that really helps. Okay. I'll show you how you would show this algebraically. which, not going to be part of this course, but suppose you end up in a real analysis course, that will definitely be, kind of the meat and potatoes of the first part of the course. So the example I wanted to do was just a nice old-fashioned one. F of x equals x squared, and the point I'm interested in is x equals 3. So, for example, and I want to show that, as we know, the limit as x approaches 3 of x squared is 9. Okay. And how we're going to prove this is going to be carefully. Okay, so what we want is, we pretty much want to find, so let epsilon be some number. And I'm going to think a little harder on this before I, start writing stuff down. All right, after careful consideration, I've decided for the length of this example, we're going to take the limit as x approaches 0 of x squared, and that's going to approach 0, really just for the algebra of it. So I'm going to just, because I know where this is headed, I'm going to say, let delta equal the square root of epsilon. Now, oftentimes this requires a little more tinkering and figuring out, what an appropriate delta for your function is going to be, or for your given epsilon. But right now, I'm going to just tell you that the square root of epsilon is where we want to go. So I'm going to say let delta equal the square root of epsilon. Okay, then what I want to show is if x minus 0 is less than delta, okay, so if I have x minus 0 less than delta, that's the same as saying absolute value of x is less than, we're saying the square root of epsilon. And then what I can do is I could square both sides, right? And I could square this, and I could say absolute value of x squared is less than epsilon. Okay? And, squaring both sides of an inequality will definitely preserve the direction, provided that both things are positive in the first place. But positive, definitely. Positive number. Okay. So what am I going to do? Oh, I think next what I'm going to do is I'm just going to observe that if I square the absolute value of a function, or the absolute value of a number, that's going to be the same as squaring the number and then taking the absolute value of it. It's not going to be any different. So, and I'm really close to what I'm hoping to show, right? I'm hoping to show that the difference between f of x and the limit is less than epsilon. Well, f of x is x squared and the limit is 0. So what I'm showing is that, x squared minus 0 is less than epsilon, which is what I'd set out to show in the first place. Okay, this was a very easy example right up there with kind of like the linear functions are also pretty easy. I have a worksheet that, it's a page clipped out of a, JIBLM workbook. And, I might link that in the description of the video if I remember to do it. But this is kind of, what you would go through to prove the existence of a limit using the epsilon delta definition. Okay, next I'm hoping to talk about limits at infinity. And so what I'm going to do is I'm going to switch to blue for the definition because I got some feedback from the Google Meet that green was a little hard to pick up. So I'm going to define the limit at infinity to be the limit as x approaches infinity of f of x is equal to L if basically we can get as close as we want to L by going just beyond a certain x threshold. And this one's, I feel like, much easier to understand. So for any epsilon greater than 0, there is a value of m. Yeah, I mean, I'm not going to say it's necessarily greater than 0. But there is a real value m where if we're beyond m, if x is greater than m, and this is because we're approaching positive infinity, you could say the exact same thing for approaching negative infinity, where if x was less than m or something like that, where if x is greater than m, then f of x minus that limit is less than epsilon. We can get as close as we want to L by taking sufficiently large values of x. That's what it means for the limit to exist as x approaches infinity. Okay, here I will draw you a little picture of this. And we know from, calculus and pre-cal that limits at infinity are what we know as horizontal asymptotes. So I'm going to just, call that the horizontal asymptote L. And we know that horizontal asymptotes, they can be crossed, all sorts of things can happen. So what I'll do is I'll say, do I really? Yeah, I'll graph it also in black. So, maybe this function is doing all sorts of weird stuff, but over time it's getting in there. So if I want to be within, I think I want this to cross fewer times and approach much more dramatically. So I think I just want one crossing of the asymptote, and then I want to be like hugging right in on. Yeah, that's what I want. Okay, so the thought is, if I want to be within some small distance of the limit, like say epsilon, and maybe I'll make the epsilon distance a little smaller this time. Okay, so this is L plus epsilon, and this down here would be L minus epsilon. Not sure if that's picking up on the camera, but I'm sure you imagine what I'm saying here. And if I want to be within kind of this lane, I just need to go beyond this x value, right? That's the idea, is that after this point right here, I'll definitely be within epsilon of my limit. And so, we can kind of trace this back to right here. And that's going to be my value of m. So beyond m, we are definitely between these two bars. Okay. And we could squeeze these down smaller, and that would just delay my m happening. Okay. So the example I want to show you is a function that we are, somewhat familiar with. And this one's got a little more analysis attached to it, but it's not going to be so algebraic. Okay, so for example, g of x is equal to sine of x over x. Okay, we know what the limit of this thing is as x approaches 0. It was a trivia fact from AP Calculus. As x approaches 0, this thing approaches 1. Okay? That evidence is also there in the Taylor series for this function, but you might not know about that quite yet. What I'm going to do is I'm proposing that the limit as x approaches infinity of this thing is 0 because it's bigger on bottom, right? Sine of x is always stuck between 1 and 1, yet this thing can get as big as it likes. So this fraction overall can get as small as it likes. So I'm going to say that the limit as x approaches infinity of g of x is 0. And you may be sitting there wondering, like, how are you going to solve for the value? Because it looks like, you just kind of need to, solve an equation right here to get an m value. What I'm going to do is I'm going to go for one that's going to be probably a little more than necessary, but it will still guarantee that we're within epsilon. So I'm hoping, So let epsilon be greater than 0. And I'm hoping to show that if m is equal to, I believe, 1 over epsilon. Okay? I'm going to take just 1 over epsilon. And I'll tell you the reason is because this function is less than 1 over x, necessarily. Okay. Or at least in absolute value. So what I'm going to say, and I'm going to let, 1 second, m equal 1 over epsilon. Okay. If x is greater than m, that's saying that x is greater than 1 over epsilon. Then I need to show that the difference between f of x and 0, so sine x over x, I'm hoping to show that this is less than epsilon. Okay, but I've got x is greater than 1 over epsilon, so let's see. Need to think about how this is going to work if, like you divide by a smaller number and the inequalities and everything. Let's see. Well, I know for sure that this is less than or equal to 1 over x, right? Because of the fact that sine of x is no more than positive 1. Okay? And then I can also say that since x is 1 over epsilon, here it is, greater than 1 over epsilon. I'm just trying to think about, oh, okay. So this will become a positive epsilon, and the greater than will become less than. And I know this is the type of inequality that, you know, because x is bigger, I'll let you think about that with some actual small numbers. You know, 0.1, 0.01, something like that.
Wouldn't that just end up being epsilon?
Yes. Yeah, that's kind of the idea. Yeah, because x is larger than 1 over epsilon. When I take 1 over that,
you're gonna get something smaller.
yeah, you're gonna get something smaller.
Mr. Rutherford?
Yes, yeah, I got a question. Yeah, the question was like, you know, that this as written is not true, and I mean, this is true. It has to do with the fact that I'm saying that because these two are equal and x is bigger than 1 over epsilon, this is definitely true. And I think I'm going to kind of just leave this example at that, because I just wanted to show you, you know, if it has to do with 1 over x and it's very bounded, you know, you're working with a bounded function, you can kind of sometimes just go with the upper bound of the function to help you with these. All right, and then the last thing I want to talk to you about is, you know, the continuity. And I had meant to not erase that, but that was the limit as x goes to infinity, so it wouldn't have been that useful anyway. I'm not going to work an example of showing that a function is continuous at a point because it more or less works the same. So remember in, you know, Cal 1 or whatever, we said that continuous meant that the limit of f of x as x approached c was equal to f of c. And that's what we're going to see in the definition. It's just we're going to take the epsilon delta definition of a limit and say that, you know, the limit equals the value of the function. So I'm going to say that I'm just going to throw down the definition, and then I'm going to end the video. So I'm going to define, so f is continuous at x equals c if for every that's a 3, not an epsilon. For every epsilon greater than 0, there exists delta greater than 0, so that if x is within delta of c, then it must be the case that f of x is within epsilon of f of c. And then we can say that f is continuous on an interval or on its entire domain if it meets this condition for every x in that interval or on that domain. And that's all I've got to say about epsilon delta.